All right, so my aim in this talk is to cover the salient points of the first two chapters of Greiwank and Walther's authoritative book on automatic differentiation, and to provide some motivation for the relevance and usefulness of automatic differentiation using the field of quantitative finance. Let's get started. Okay, so as I said, I'm going to start with a motivating example that comes from quantitative finance. After that, I'm going to define at a very high level what automatic differentiation is. Then I'll move on to the contents of the chapter. So this begins with what we can call a model of computer evaluated functions from Greiwank and Walther. So this is sort of the abstract model of a computer function that the authors use and to which they apply their automatic differentiation algorithms. From there, we'll move on to discussing forward and reverse mode, the two primary modes of automatic differentiation, in some amount of detail, though still at a fairly high level, and we'll relate those back to our motivating example. Finally, we'll discuss some additional high-level concepts from the chapter, which I found to be of interest. Let's proceed. Okay, so we're beginning with the motivating example. Okay, and here we have a quote, and the quote is from an industry group called the Counterparty Risk Management Group, and it says, credit risk, and in particular, counterparty credit risk, is probably the most important variable in determining whether and with what speed financial disturbances become financial shocks with potential systemic traits. And on the bottom of here, on the slide, I've got some headlines from the 2008-2009 financial crisis. This was certainly an instance in which a financial disturbance in the mortgage-backed security market had wide-ranging systemic effects. Okay, so let's think a bit more about this quote, and let's pick apart what it's talking about. Okay, so the quote is talking about counterparty credit risk in the OTC derivatives market. So first, let's talk about what are OTC derivatives. So first of all, they're derivatives, which means that they're financial contracts whose value is derived from some underlying economic quantity. So this could be shares in a company. This underlying quantity could be an interest rate, or it could be a commodity like oil or natural gas or orange juice, any number of things. So a derivative, it has some value that depends on the underlying quantity, hence the term derived. Probably the most familiar forms of derivatives to most people are call and put options, which are basic forms of derivatives on shares in a company, on equity, as we say. So that's what a derivative is. Now, what's an OTC derivative? So here, OTC stands for over the counter. And this is in contrast to exchange-traded derivatives. So OTC derivatives are not traded on a centralized exchange. Instead, they're negotiated directly between the parties involved. And they're customized to meet the needs of the two parties. Okay, so that's what an OTC derivative is. It's a financial contract derived from an underlying economic quantity, and it's one that's traded over the counter, not on an exchange. Okay, so then this quote that we were looking at is talking about counterparty credit risk. So what's that? Well, because they're not traded on an exchange, OTC derivatives have this form of risk called counterparty credit risk, which is the risk that the counterparty, that is the person on the other side of the derivative contract, will not fulfill their obligations. So for example, it may be that you and I enter into a financial contract that says that for the next 10 years, you will continue to pay me some rate that's determined by some formula based on market observations. But maybe 5 years into this 10-year contract, you go bankrupt. Then, even though the contract says that I should continue to receive payments from you for the remaining 5 years, I do not in fact receive those payments because your corporation has gone bankrupt, so you're not around to make those payments. Now, this form of risk, this counterparty credit risk, that is an aspect of OTC derivatives, is blamed for amplifying the financial crisis in 2008. And it's blamed largely due to a phenomenon known as contagion. So in contagion, what happens is you can think of having a graph of financial entities where the nodes on the graph are the entities and the edges are OTC derivative contracts. Then on this graph, the bankruptcy of one entity will cause the spread of financial disturbance to all its OTC derivative counterparties along the edges of the graph. So in other words, there can be a propagating and cascading financial disturbance. And this sort of problem is what worries regulators. And consequently, the Basel Committee on Banking Supervision requires that banks take into account and hedge counterparty credit risk. And indeed, it's in their own interest to do so. Okay, so let's think about how we should manage counterparty credit risk. So we talked about the importance of it, why it's important, because of the potential for contagion. So now let's discuss how do we measure it first, and then we'll discuss how do we manage it. So measuring of this risk is actually extremely complicated, and there's many long and very technical books written on the topic. But this slide, which contains a graph from a very interesting article, I'll link it in the description. This slide talks about it at a very high level. So broadly speaking, the approach to quantifying counterparty credit risk is as follows. So we simulate the distribution of some market variables going into the future. And then we do many of these simulations. So we have many sort of future paths of the market, many potential paths the market can take. And then on each future date, on each of the paths that we've simulated, we revalue our entire portfolio and compute our exposure to counterparty credit risk. That is, on that future date, if the market takes a path that we predicted according to one of our simulations, how much do we stand to lose on that future date if our OTC derivative counterparties go bankrupt? Okay, so we do all these simulations. We compute our exposure to counterparty credit risk in the future on these simulations. Then what we do is we aggregate back to the present all those potential losses we computed on those future simulations. So we aggregate them back to the present to come to one number. And this number resulting from aggregating potential future losses to the present, this tells us sort of an adjustment to the value of our derivatives to account for these potential future losses. And this adjustment is known as CVA, or credit value adjustment. So for example, suppose that we have a derivative which on its face is worth $10. Well, it may be the case that once we do this CVA calculation, we get a CVA number of $2, which would then tell us that actually we should subtract 2 from the value of that derivative and only value at $80 because of potential future losses due to counterparty credit risk that we may incur. So then this at a high level is the idea of CVA, which is used to quantify counterparty credit risk. Okay, so that slide was about quantifying counterparty credit risk. Now let's discuss hedging counterparty credit risk. So it's not enough to know how much counterparty credit risk we're exposed to. additionally, we want to protect ourselves against it. So the standard approach to this is, well, we take the CVA, which we computed previously, and we compute its partial derivative with respect to various market risk factors, which might include sort of yield curves describing for current and future interest rates, or FX rates, or volatility surfaces describing option prices, and so on. So we compute the partial derivative of CVA with respect to all these market variables, and then we try to change the makeup of our portfolio so that these partial derivatives are small. And the reason for this is that then if the partial derivative of CVA is small with respect to these market risk factors, then if the market moves, it's unlikely that CVA will change significantly, because just by the definition of a derivative, the sensitivity of CVA to these market risk factors is small. So you can think of this as hedging based on a first-order Taylor approximation. So we work out a first-order Taylor approximation to CVA, and then we adjust the constituents of our portfolio to make sure that according to that first-order Taylor approximation, we are unexposed to market movement. So this sort of first-order Taylor approximation-based approach is very common in quantitative finance. Okay, so that's how we hedge counterparty credit risk. We compute these partial derivatives. Okay, let's look at an example of this. So suppose, just to make up some random numbers, suppose that we have a yield curve that's represented by 70 different points. So we've discretized our yield curve into 70 points. And maybe we have 10 of these yield curves, because maybe we have one yield curve, we have a few for different currencies, and maybe we have multiple yield curves even within a single currency to correspond to different interest rates relevant to that currency. And maybe you also have a volatility surface with 30 strikes and 30 maturities describing some option prices of interest to our portfolio. Now, suppose that we take the approach described in this previous slide, and we want to compute partial derivatives to these market risk factors. Well, we're going to need to compute something like 1,600 partial derivatives to know how we need to hedge our CVA, because we have 1,600 market inputs here. Now, suppose that we take this traditional approach here called bump and reval. And what is bump and reval? Well, it's just based on the first-year calculus definition of a derivative. That is, we compute CVA at the current market state, and then we compute CVA at a slightly perturbed market state, CVA at x plus h, subtract the 2 and divide by h for some small h. Now, as h goes to 0, this becomes a derivative, but for small but finite h, this is an approximation of a derivative, a finite difference approximation. Now, the problem is, if we take this approach, then we need to compute x plus h 1,600 times for different perturbations corresponding to the partial derivatives we're interested in. And we already said that computing CVA is extremely costly because it requires this massive simulation. So now what we're talking about is, in order to compute the relevant derivatives, repeating this massive simulation something like 1,600 times, which is extremely costly, probably prohibitively costly. So what happens if the market moves unexpectedly during the day and we want to re-hedge? Well, we need to recompute our Taylor approximation, so we need to recompute all these partial derivatives. But if we use this approach, it'll be too costly to do in any reasonable amount of time, and this might result in sort of trading blind or unexpected losses. So this is not an ideal situation. Okay, so this whole motivation section based on quantitative finance, it brings us to this point, which is, well, we have this problem of computing partial derivatives for CVA, and if we take this finite difference approach, it's too costly. But there's an alternative approach, and that is, if we use reverse mode automatic differentiation, then the time required to compute the gradient of a scalar function, i.e. all its partial derivatives, is no more than about 4 times the time required to compute the base function itself. And so this is a strong contrast with the previous approach, which took 1,600 times more work. This is only going to take at most 4 times more work. And this provides a strong justification for the relevance of automatic differentiation to this kind of application in quantitative finance. Now, obviously, or as we'll discuss maybe in some other talks, automatic differentiation has a huge range of applications, but I think this is a strong one to start out with. Okay, so what is the main idea of automatic differentiation at a high level? Well, at a high level, it's very, very simple. That is, you just write your program, your computer program, as a sequence of elementary operations. And the key thing about these elementary operations is that they're sufficiently simple that we know how to differentiate them analytically. Then, since we've written the entire program as a sequence of these elementary operations, we differentiate the entire program via chain rule. And that's it. That, at a high level, is the main idea of automatic differentiation. Now, there are some subtleties, well, actually quite a few subtleties, and we'll go into a bit more detail in this talk, but we'll still be covering just the broad strokes. Okay, so let's get into Greiwank and Walther's first 2 chapters. So one of the first things that they discuss is a model of computer evaluated functions. That is, well, if we want to apply chain rule to our computer programs, we need to express them in the right form. And so this section is about expressing them in the right form. Okay, so the summary of Greiwank and Walther's sort of model is this 3-stage flowchart shown at the bottom of this slide here. And it consists of the steps where you start with a program, then you convert it to an evaluation procedure, and then you convert the evaluation procedure to a trace. Okay, so from their point of view, a program is just a general computer program, but now let's talk a bit more about what they mean by the subsequent 2 stages. So in an evaluation procedure, some of the inputs to the computer program are nominated to be independent variables. And then there are other inputs that are sort of not declared to be independent variables. So what's the significance of this? Well, the significance of this is, first of all, when you're performing automatic differentiation, you're only going to consider differentiating with respect to those inputs that you consider independent variables. So there may be other inputs, but those other inputs are sort of not viable candidates for differentiation. So one example of this might be, suppose that you have a PDE or partial differential equation solver. And suppose that you fix the grid spacing in that solver. So then the grid spacing, even though it's an input to the program, it's not considered an independent variable. But maybe you nominate the initial condition as an independent variable. So in this case, you can differentiate with respect to the initial condition, but you can't differentiate with respect to the grid spacing. And furthermore, they're going to add the condition that if you have sort of if statements in your code, basically like if you have conditional statements, then those statements, they can't depend on inputs which are independent variables. So in this case, in our PDE solver, we couldn't have if statements depending on initial conditions or things that depend on the initial condition. And actually, this is quite a restrictive assumption. There's exclusion of control flow based on independent variables. And it's only an assumption they impose sort of at the beginning of the book. Later in the book, they discuss ways of relaxing this assumption, which allows the treatment of much more general programs via automatic differentiation. Yeah, so that's just a note on that, which seems quite exclusive, but then this assumption, but then it's going to be relaxed later. Okay, so that's what an evaluation procedure is. So we start with a program, we nominate our independent variables, which gives us an evaluation procedure. And then the last step is before the actual automatic differentiation is transforming the evaluation procedure to the trace. So when you transform an evaluation procedure to the trace, it just amounts to substituting specific values for the independent variables. Okay, so this is sort of the model of computer evaluated functions Greiwank and Walther use. Okay, so let's talk a bit more about the notation the authors use to describe evaluation procedures. So in their evaluation procedure, they denote the inputs, i.e. the independent variables, as xi's. They denote the intermediate variables as vi's, and they denote the outputs as yi's. So these first three lines here. And furthermore, they use this notation here, I squiggly less than j, to denote that intermediate variable j depends on intermediate variable I. So in order to compute intermediate variable j, you need intermediate variable I. And they also use this notation here, phi I, to denote the elementary function that's used to compute intermediate variable I. And remember, the key thing about elementary functions is that we know how to differentiate them analytically. Okay, so then in this table 2.2, they have this sort of very high-level abstract view of what an evaluation procedure looks like. So there are three stages. In the first stage, you take your independent variables, your inputs xi, and then you initialize the first intermediate variables. In the second stage, you repeatedly compute intermediate variable vi using the function, the elementary function phi I. And note that whenever you're computing intermediate variable vi using phi I, you're doing so using only those inputs j, which are squiggly less than I, which denotes the fact that you're only using intermediate variables upon which intermediate variable I is known to depend. Then once you proceeded through the program and computed all these intermediate variables 1 to L, then the final step consists of just assigning the output variables, the y's, based on the final intermediate variables. And then you have the output variables, and so you've completed evaluating the evaluation procedure. So this is a very simple model of an evaluation procedure. We just start out with some inputs, then repeatedly apply elementary functions, and then we end up with our outputs. Okay. So note here we use this sort of squiggly less than notation, I squiggly less than j, to denote a dependence between intermediate variable j and I. That is, you need to know I to compute j. So there's another way to express this relation, and that is a computation graph. So in the computation graph, you draw a vertex or node for each intermediate variable, and then you connect a directed edge from intermediate variable I to intermediate variable j if intermediate variable I is squiggly less than j. So that is, the edge from I to j denotes a dependence from j on I. And this graph contains exactly the same information as you would get by this squiggly less than relation. And this computation graph representation is actually quite popular, quite a popular point of view. And it can reveal some interesting things. I think this is particularly popular in machine learning literature on automatic differentiation. Okay, so now to sort of illustrate an example of an evaluation procedure, Greiwank and Walther give this sort of simple example of an evaluation procedure whose purpose is to compute this simple mathematical function here at the top. So they have this function here, and then they have basically the sequence of steps. So notice that there's two inputs, x1 and x2, and one output, y. So they start by assigning intermediate variables v negative 1 and v0 based on x1 and x2. And then they just apply a sequence of elementary functions, one after the other, to compute all the relevant intermediate variables. And at the end, they get the output y using intermediate variable v6. And you can verify that, in fact, this program, this evaluation procedure, does in fact compute this mathematical expression at the top. Okay, and maybe one point to observe here is that common sub-expressions are used. So for example, x1 over x2 occurs in a few places in this expression, but this is not recomputed multiple times in this evaluation procedure. Instead, it's computed once and then used a few times. And so this is sort of an important consideration for efficiency in practical programs and practical automatic differentiation. So what we just discussed on the left, that's the evaluation procedure. And then on the right is the trace. And the trace is computed, as we said. Remember, what is the trace? The trace comes from substituting specific values for the independent variables. So then on the right, we substitute specific values for the independent variables, which implies specific values for the intermediate variables, which in turn implies a specific value for the output variable. And this gives us the complete trace. Okay, so that's the baby example of an evaluation procedure. Now, furthermore, I thought it would be interesting to just look at this same example using a modern automatic differentiation framework. So I chose to use JAX, which is sort of a popular research AD framework. So in this example, we just define a function in Python using basically the steps from this evaluation procedure. And then what you can do in JAX is you can call a JAX function called make JAXPR on baby function, this function we define. And make JAXPR just shows you JAX's internal representation of the function. So recall that in an evaluation procedure, you need to write your function as a sequence of elementary operations. So then when you call make JAXPR, you can see the sequence of elementary operations into which JAX has decomposed your Python function. So here, this just shows the elementary operations JAX is using to understand the baby example. And it's pretty close to what we have on the previous slide. Okay. Now let's talk about forward mode in automatic differentiation. So one of the two main modes. Okay, so what's the goal of forward mode? Well, the goal of forward mode is we have our evaluation procedure and we want to transform the evaluation procedure via the chain rule. This being consistent with what we said is the main idea of AD. So we write a program as a sequence of elementary operations, so we can check that off. That's just an evaluation procedure. Then we want to differentiate via chain rule. So the first approach we're going to try to step 2 is forward mode. Let's go back to where we were. Okay, so we want to transform our procedure via chain rule, and we want to get a new evaluation procedure after the chain rule transformation that has a complexity similar to the original program, a computational complexity. Okay, and what's going to be our approach? Well, our approach is going to be, we're going to pick an input variable or a weighted sum of input variables. And then for each intermediate variable in our sequence of intermediate variables in our evaluation procedure, we're going to compute the derivative of that intermediate variable with respect to the chosen input. And then at the end, this will give us the derivative of the output variable with respect to the chosen input. Okay. So we started, remember we had this sort of abstract general model of an evaluation procedure. Now we can look at what is the abstract general model of the evaluation procedure after we've transformed it via forward mode. Okay. So let's get started and looking at this. So first of all, note that just as we had before, here in this transformed procedure, we have 3 stages. And furthermore, note that each stage consists of 2 steps. And the first step of each of the 3 stages is identical to the corresponding step in the original evaluation procedure. That is, the original evaluation procedure is still here. We've just interleaved some auxiliary steps that have been added by forward mode automatic differentiation. So let's look at these interleaved steps one at a time. So first of all, in the first phase, where in the original step, we just assign our initial intermediate variables based on our input variables, here we correspondingly assign sort of variance, these sort of dots intermediate variables. So in forward mode, for every intermediate variable vi, we introduce a new intermediate variable vi dot based on the derivative, that's the derivative of that intermediate variable with respect to the chosen input, because remember, that's our plan. So here we just assign the initial vi dots. And so suppose that we select, say, xk as the input to with respect to which we want to differentiate. Then we say, then when we're picking these xi dots for the initial inputs, we would say that xk dot equals 1 and all the other xi's are equal to 0. That would signify that it's xk with respect to which we want to differentiate. Okay, so that's the first step. So we just assign initial intermediate variables, vi's, and we also assign the vi dots. Okay, let's go on to the second stage. So in the second stage, as before, we're computing vi based on elementary function phi I. And note that elementary function phi I depends on the j's that are squiggly less than I. Okay, but in addition, there's another step that's been added by forward mode automatic differentiation. So here we assign vi dot. And how do we assign vi dot? Well, using this formula here on the right-hand side. But this formula, it's just chain rule. This is exactly chain rule. So what are we doing here? Well, since we're proceeding forward through the intermediate variables, we know that we've already computed vj dot. So we already know for all the j upon which I depends, we already know the derivative of those j intermediate variables with respect to the chosen input. So we already know the vj dots. We're just going to compute vi dot. And the way we do that is we just sum over all the j's upon which I depends, and we take the derivative of our current elementary function with respect to vj and multiply by vj dot. So this is exactly chain rule. That is, we have some derivatives of inputs to phi I with respect to our chosen input. And then we want to get the derivative of the output of phi I with respect to our chosen input. And we can do that by propagating forward using chain rule. Okay, so then using this procedure, in every step we compute vi, that is the ith intermediate variable, and we also compute vi dot, which is the derivative of the ith intermediate variable with respect to the chosen input. And then in the last stage, as before in the original evaluation procedure, we assign the outputs y, but we also assign the y dot outputs, which are the derivatives of the outputs with respect to the chosen input. Okay, so that's sort of the general evaluation procedure. Now remember, before we had this baby example illustrating an example evaluation procedure. Now we can see what happens when we apply forward mode to this baby example. Well, as you would expect, we just start out as before assigning x1 and x2, but then we also assign x1 dot and x2 dot. And here note that we've set x1 dot to equal 1 and x2 dot equal 0, indicating that we want to differentiate with respect to x1. And then we have the same evaluation procedure as before, except that whenever we compute a vi, we also use the chain rule to compute the relevant vi dot. So here we're computing v1, but we're also computing v1 dot using our knowledge of how to differentiate the appropriate elementary functions. And when we compute v2, we compute v2 dot as before, since we know that the derivative of sine is cos. And this continues, et cetera, until we get to the very end where we compute the outputs. And we also compute the output dot, that is the derivative of the output with respect to the chosen input. And so that's the transformed evaluation procedure. And on the right, we can see the transform trace, which results from substituting specific values for the independent variables and correspondingly getting specific values for the other variables. Okay, and then just as before, we could look at what does this look like in JAX. So here we have our same baby example function, and then we can call jax.jvp, which is how you apply forward mode automatic differentiation to a function in JAX. And you can see that you get a new transformed function, and you can call make JAXPR on that transformed function to see the elementary operations that constitute the new transformed function. And if you look back here, you can see that these roughly correspond to the transformed elementary operations given in the text. Okay, and then another comment on forward mode automatic differentiation is that the fundamental mathematical operation underlying forward mode automatic differentiation is the Jacobian vector product. So one way to think of this is that we start with some original function f that goes from an m-dimensional vector space to an n-dimensional vector space. Then when we apply forward mode, this transforms it to compute f dot. It gives it f dot, which is a new transformed function. And this new transformed function, it accepts different inputs. It accepts x as before, but it also accepts x dot. And it outputs f of x as before, but it also outputs f prime of x times x dot. That is the Jacobian of f times this vector x dot that we passed in at the beginning. So this Jacobian vector product is basically a directional derivative in the direction x dot. So basically forward mode automatic differentiation lets us compute a function and additionally compute its directional derivative in some chosen direction. Okay, so let's think about this. Let's think about what did we just do? Well, we transformed f into this transformed function, as we said, but does this actually solve our original problem? So remember, if we go way back up here, what was the original problem? Original problem was we wanted to differentiate CVA with respect to a ton of market variables. So if we go to our comments on forward mode automatic differentiation, we can see that forward mode, unfortunately, does not actually solve this problem. Why? Because every call to the forward mode transformed function gives you the directional derivative in one direction, which means that if you want to differentiate with respect to 1600 inputs, well, you need to call the transformed function 1600 times. In other words, you want to compute every column of this Jacobian, but in a single call, you only get one column. So you need to call the transform function many times, which is very inefficient, just as inefficient, in fact, as the finite difference approach we were talking about before. So that's the drawback of forward mode. But on the other hand, forward mode does have an advantage, which is that basically, suppose that we have a function with a large number of outputs, then a single call to the forward mode transformed function will give us the derivative of all those outputs at once. So in this sense, forward mode is good for functions which have a large number of outputs, but not good for functions which have a large number of inputs. Okay, and what's the time and memory cost of forward mode? Well, they're roughly the same as the original program, and I'll just comment that at a high level you can see this because what have we done? We just interleaved some extra steps in addition to the steps that were in the original program. And so you can think that time and memory usage will only go up by some constant factor. Okay, so we said before that forward mode unfortunately doesn't solve the original program, the problem that motivated us. But now we can talk about reverse mode, which will solve this problem. And so what's the approach of reverse mode? Well, in forward mode, remember, we picked an input variable, and then we computed the derivative of all intermediate variables with respect to that input variable. So reverse mode, we can think of this as sort of taking the dual approach. So in the reverse mode, instead of picking an input variable, we pick an output variable. And then for each intermediate variable, we compute the derivative of the chosen output with respect to that intermediate variable. Okay, And so just as we showed how you transform the general evaluation procedure to get the forward mode transformed evaluation procedure, so we can show how you get the forward mode transformed, the reverse mode transformed evaluation procedure. And where before for each intermediate variable vi we added vi dot, here we're going to, for each intermediate variable vi, we're going to add vi bar. And vi bar, remember, is going to denote the derivative of the chosen output with respect to intermediate variable vi. Okay, so now let's examine in a bit more detail this transformed evaluation procedure. So first thing to note is that there's a contrast between the forward mode evaluation procedure and this. So in the forward mode transformed evaluation procedure, recall that we were sort of interleaving extra steps. So for each original step, we added one extra step immediately after. Now, if we go to the reverse mode transformed evaluation procedure, that's not the case. Instead of interleaving steps, we now have sort of two phases. So the first phase, we just have all the original steps. So this replicates the original evaluation procedure. And then in the second phase, we have entirely new steps. That is, so yeah, as I said, instead of interleaving, we now have just two phases, one phase consisting of original steps, one phase consisting of new steps. And then let's discuss how this works. So we just do the original evaluation procedure here. And then when we get to the end of the program, we now start working backwards from the end. So we can see that, well, first we start out by defining the y bars. Remember, before we were starting out by defining x dot. So here we start at the end, defining some y bars. And if we want, so we define these y bars, and then we're going to step backwards. So if we want to say that we want to differentiate one chosen output, say yk, then we would set y bar k equal to 1 and all the other y bars equal to 0. Okay, and then we compute the vj bars for all the intermediate variables vj. And how do we do that? Well, this is just by the chain rule. So here, when we want to compute vj bar, because we're stepping backwards now, we assume that we already know the vi bars for all i's that are squiggly greater than j. That is, for all i's that depend on j. And so then, when we want to compute vj bar, we just use the chain rule. That is, we just sum over all these later intermediate variables which depend on I. We sum over the derivative of our chosen output with respect to those later intermediate variables. So we already know these vi bars, and we multiply them by the derivative of the relevant elementary function that was used to compute vi with respect to vj. And then we just complete this sum. So this is the chain rule because we already know sort of these downstream derivatives. We already know the derivative of the chosen output with respect to the variables that depend on vj. And then we can use the chain rule to propagate that back to vj itself, which then gives us the derivative of the chosen output with respect to vj. And then we can just repeat this process going from the end of the original evaluation procedure to the beginning. And then once we've gotten to the beginning, we can then just assign the xi bars, which are the derivatives of the chosen output with respect to our independent variables. Okay, so we step backwards, computing all the vi bars, and we end up with the xi bars. And I guess this description of the procedure is called non-incremental because sort of in one step here, we aggregate the contributions from all the downstream intermediate variables that depend on the current intermediate variable vj. There's another completely equivalent way to write this, which is called the incremental reverse procedure, which just means that instead of considering all at once all the downstream intermediate variables that depend on vj, we consider them one at a time, but the result is the same. And just as before, we looked at the baby example in the after applying the forward mode transformation. So here we can look at the baby example after we apply the reverse mode transformation. And just as we saw in the abstract case here, where we had two phases, so we have two phases here. We have this first phase where we compute the original evaluation procedure, and then we compute all the VIs. Then we have the second phase where we compute all the VI bars. Okay, and then just as before, we saw the forward mode transformed evaluation procedure as represented in JAX. So here we can see the reverse mode transformed evaluation procedure as represented in JAX. And so here we just call jax.vjp, which is how you get reverse mode in JAX. And then we can call make JAXPR to look at all the elementary functions that make up the reverse mode transformed evaluation procedure. And you can see them listed here, and they correspond pretty closely to what's in the text. Okay, and then just as before, remember before we saw that the Jacobian vector product is the fundamental mathematical operation underlying forward mode automatic differentiation. So here we can see that the transposed Jacobian vector product is the fundamental mathematical operation underlying reverse mode automatic differentiation. So we start with some original function f, and then reverse mode gives us f bar, which is transformed because it takes as input x, but also y bar. And then what is the output? Well, the output is f of x like originally, but also f prime transpose, that is the Jacobian transpose times y bar. Okay, so now we can see that, in fact, what we've just done, this reverse mode automatic differentiation, it actually solves our original problem. Why is that? Well, because in a single call to reverse mode automatic differentiation, we get the derivatives of the chosen output with respect to all the inputs. That is, we get all the xi bars. And so if we were to apply this to our CVA, our credit value adjustment case, this would give us many derivatives in a single call. And you can see this from this transposed Jacobian vector product approach, because before, the problem with forward mode is we were taking the Jacobian and then we were compressing the inputs. We were multiplying it by a vector on the input side, which meant that we only got sort of we only got sort of one scalar of input derivative information per call. Now we're multiplying not the Jacobian, but the transposed Jacobian by a vector. So in other words, we're compressing the Jacobian, but we're compressing it on the output side, leaving the input information in the Jacobian uncompressed. And so this relates to our observation that we're getting derivatives with respect to all inputs in a single call to the reverse mode transposed function. So this is great. It solves our problem, but we can notice there is a drawback here. And that drawback is, suppose f is a vector function and we have many outputs and we want to differentiate each of the outputs of f. Well, then we need to make a call to the transformed function once per each of the outputs of f. Because after all, as we saw, in reverse mode, we compress the output part of the Jacobian. So there's a trade-off, but in many cases, this trade-off is worth it. And so, for example, in the CVA case, we have many more inputs than outputs. We only have one output. So clearly, reverse mode is the optimal choice there. And this occurs also in machine learning, for example, where you may have a loss function that's a single scalar, but millions of weights as your input. And in that case, reverse mode is clearly the optimal choice. Okay, let's discuss the performance characteristics of reverse mode automatic differentiation. So first of all, time is of the same order as the original program, because we're just adding one step per each step of the original program. So we're going to get a roughly constant factor increase in amount of work. But there is a strong contrast with forward mode in terms of memory usage. And that is, well, note that when we're doing this backward pass here in the forward mode automatic differentiation transformed program, note that we may need to access variables that were allocated in the original evaluation procedure, that is in this first phase. And as a consequence of this, we can't just immediately sort of deallocate intermediate variables in the original program when we no longer need them later in the original program, because we may need them in this backward pass. And so this has sort of some unfavorable implications for memory usage. In particular, we could incur additional memory usage on the order of the number of steps in the original program, because at worst, we may need to save all the intermediate variables computed in the original program for use in the backward pass. And so this is sort of a downside of reverse mode automatic differentiation. Okay, so we covered forward and reverse mode, and we related how reverse mode solves our original motivating example of needing to differentiate CVA with respect to a lot of inputs, but has some unfavorable memory usage characteristics. Okay, so now I just want to talk about some additional concepts that came up in these first two chapters of Greiwank and Walther. So one concept is this of code quality independence. So throughout their book, Greiwank and Walther have a number of rules of thumb about sort of what is good practice, and or at least what are their observations from their many years of experience on how you should do automatic differentiation and how automatic differentiation tends to work. And so one of their rules of thumb here is this rule of code quality independence, which basically says that what's good for function values is good for the derivatives. And one way to understand that is, well, you could have an original function that may have certain characteristics. It may be sort of more or less efficient. It may have good or bad numerical stability. And their comment is that, in general, the transformed program, after you apply forward or reverse mode automatic differentiation, will inherit sort of the numerical stability and efficiency of the original program, which is good news, because it means that we only need to focus on writing the original program in sort of a stable and efficient way. And then the transformation will sort of ensure that the transformed program inherits these characteristics. So it's less for the programmer to worry about, and this is sort of a win for automatic differentiation. Okay, this extended system, it was interesting. In the interest of time, I think I'm going to skip it for now, but I may return to it in the future. Okay, so then here's this table about elementary functions. So we mentioned that the fundamental aspect, the fundamental key to automatic differentiation is writing your program in terms of elementary functions whose derivative you know. So we didn't actually enumerate what those are, but they list some here. And they have several sort of categories of elementary functions. So the simplest elementary functions are just sort of basic arithmetic operations: add, subtract, multiply, and then some basic transcendental functions like exponentiation and the trigonometric functions, etc. And these are functions whose derivatives are known and which can be used to write a wide variety of more complex functions. But they also comment that there are sort of extensions of this to which you can apply automatic differentiation, which they do explore in the later chapters of the book. So the first extension is considering not just smooth functions, but functions which are only Lipschitz continuous. And so one example is the absolute value function, another are the min and max functions. And then a further extension you consider are functions that are not even in fact continuous, like the Heaviside step function. And a comment I'll make here is that if we get to the point where we can add the Heaviside step function to our arsenal of elementary functions, then actually we resolved one of the original problems we noted way at the beginning here. And that problem we noted was that, where is that? It's back here. We noted that we were excluding control flow involving the independent variables, which kind of severely limits the number of programs we can consider. But then if we extend our set of elementary functions, as they do here, to include the Heaviside step function, then we can basically recover the ability to do control flow, because any control flow we may be interested in can be implemented in terms of the Heaviside step function. Okay, and then another comment they make is that, well, these elementary functions here are basically scalar functions, but you may want to also consider vector elementary functions, which operate on sort of many inputs at once. And indeed, this is how the most powerful automatic differentiation frameworks used in sort of modern tools work, especially the ones targeted at machine learning use cases. So just to interact well with modern hardware, it's necessary to perform vector operations. And given that, it's highly desirable to have an automatic differentiation framework whose primitive elementary functions are in fact vector functions. And that's what sort of modern AD frameworks do, like PyTorch, etc. Okay. And then this last slide is just a table I made based on some comments that the authors make comparing various forms of automatic differentiation, various forms of computational differentiation, I guess you could say. And so these three forms they list here, and then they compare some sort of aspects of these three types of differentiation. So the first one is numerical differentiation, which is this bump and reval approach we discussed at the very beginning, based on the divided difference definition of derivative. And so its mechanism is divided difference, and its result is a number. Another form of computational differentiation is symbolic differentiation. And this is basically the automatic algebraic manipulation of some expression via chain rule. So again, its mechanism is the chain rule, and the result is not a number, but a transformed symbolic expression representing the derivative of the original expression of interest. And then the third form, and the interest, the focus of the book we're currently talking about, is automatic differentiation. And here, like symbolic differentiation, the mechanism is a chain rule, but unlike symbolic differentiation, the output is not an algebraic expression. Instead, the output is a number, just like numerical differentiation. Or if you think of it another way, the output is maybe a transformed program. So you start with one program and you produce a new transformed program, which you can then get numbers out of. So I just thought this sort of comparison was enlightening and sort of segregated some terms that are often muddied and confused. Okay, thanks for listening to my talk. I hope you found it useful.